Good morning, everyone. Just to inform you that I've started the recording. Does anybody have any questions? Any questions of the topics we have covered as of now? How is the course doing? Any comments on that? Any suggestions? Any modifications you wish to incorporate? Nothing at all. We will wait for a couple of minutes. I hope we touch 100. Hopefully, much more than that. Okay, the last time, any questions on any of the lectures? Any concept that was not clear? Want me to repeat it? Anything? Okay, so let's continue. It's nothing from your end. I hope the screen is visible.
Yes.
Okay, thank you. Right, today is the 6th lecture. Remember group 5, ID number 25 to 30. You're supposed to take notes, prepare them, and submit. Okay, do we have ID number 25 in the meeting?
Yes, sir.
26.
Yes, sir.
27. ID number 27, are you there?
Oh, I'm sorry, sir. I heard 36, not 26.
Okay, now ID number 26 is, are you there? Okay, 26, not there. 27, not there. 28.
Yes, sir.
You're 28, right?
Yes.
Oh, 29. 30?
30 present, sir.
Thank you. Right, so let's get started without wasting time. So before we move on to the next main topic, there's a couple of concepts, couple of definitions mainly that are left. The first thing is what is called the centralizer. Let me give you the definition. So let's say there is some group G, right? And pick any random element, call it A. Okay, then we have something called the centralizer of this element A in the group G. Okay, it is denoted by CGA. G is the group and A is the element we are considering right now. CGA is the set of elements in the group that commute with the element A. Okay, so this is the definition. CGA is the set of all x's or all elements in G such that x commutes with A. Is that clear?
Yes, sir.
So let's pick up an example. Right, so this is the group B3. Symmetries of an equilateral triangle. Let's give the group table here. Let's just randomly pick an element here. It's CG of I. What would this be?
All the elements.
All elements, right? And this is true not only for D3 but for any group. Just by definition of identity, an element that commutes with every other element of the group, irrespective of what the group is. This is sort of a special example. Let's take another one. In particular, that everybody wants me to pick up. Would be one rotation and one. Let's say EG R2. What elements commute with R2?
I and R1.
I and R1. Anything else? There's at least one more element.
R2. R2.
That again is true for any group, isn't it? CG of A. Two elements can always specify for any element and for any group. Which are there? One is identity of course, and itself. They will always belong to the centralizer of that particular element. Okay, so this is one example. Let's take centralizer of one of the flips. Yes. Identity for sure belongs. FC also would be an element. Anything else?
No, sir.
No.
No, sir.
So again, you can see that this centralizers, at least in this example, are special, right? They are not random sets. Know what this set is. This set. Both of them are
Subgroups of.
is that a coincidence? That maybe it is the example that we chose, because of which the centralizer of these two elements, and even of course in this case, so the centralizer of these three elements come out to be subgroups. Okay, how about an abelian group, by the way? B is an abelian group then. What can you say about the centralizer of any element?
Whole
Same
group.
set.
Will be whole group.
G.
Still, the centralizer is a subgroup of the group. Right? So the natural question is this just a coincidence or is this a result that we can prove? It is your next proposition. I claim that any group and any element, the centralizer of that element in the group has to be a subgroup of G. Okay, so somebody help me to prove this. So what are we supposed to prove here?
Closure and inverse.
Closure and inverse. So let's take closure first. Okay, so let's say we have two elements B and C in CG of A. What are we supposed to show?
B dot C is in CG of A.
So that BC belongs to CG of A. So what do I have to show in order to prove that BC is in CG of A?
A dot BC is equal to BC dot A.
C. Okay, how do I show that? A, BC is speak up, but it's not very difficult to see what should the next step be. Do I do? See, I know B and C are already elements of the centralizer, so I should
So
use that, right?
this
Associ-
A dot B. We should
Right,
take
so-
A, B in bracket.
Associ-
Right, associative. Then what is AB?
BA.
A, B, B, A.
BA. This is
Again associative.
an associative. AC. What is AC?
This is A.
This right, so we are done. Next, inverse. So again, let E be any random element is the centralizer of A. Okay. Go ahead, who would like to try this out? What does this mean? That P is in the centralizer of A.
A dot B equal to
P dot A. Then what should I do? See, what do I want? I want AB inverse equals B inverse A, right? So how do I get that? So pre-multiply and post-multiply by B inverse on both sides. Okay, what would that give me? B inverse AB B inverse equals B inverse BA B inverse, right?
Yes, sir.
What does this imply? B inverse A. B into B inverse is identity. Forget that. B inverse B is again identity. So, B inverse implies that B inverse is also the centralizer of the element A. Or centralizer of any element is a sub.
Sir, statement centralizer of a subgroup of G.
Right.
Instead of it, we can say that centralizer of any element is abelian subgroup of G. Right?
So is that right? So do you think two elements of the centralizer will commute with each other?
No, sir. It will
Sorry, sir.
be not with each other.
Right? I mean, not necessarily.
Yes, not necessary.
Now, again, please don't be sorry. It's a valid question. And to be honest, I didn't think about this question. Right? So please feel free to raise questions. Okay? I mean, I am teaching this because I want to learn this, not because I am an expert in this. Right? And unless you ask questions, I may not be able to learn much. Okay. So anyways, let's go ahead. So centralizer of one element is a subgroup, right? Let's sort of stretch it a little more. Stretch it in the sense we are going to now look at the concept of center of a group. Okay, so let's first look at the definition. Okay, the definition is let G be any group. Okay, the center of that group is denoted by Z of G. It's nothing but the set of all elements that commute with all elements of the group. Okay, so there is a small difference between center and centralizer. Perhaps because of that, they have been given similar names. Okay, so Z of G, nothing but the set of all elements of the group X over here, such that X commutes with each and every Y that is in the group. Okay, so in centralizer, that elements of the centralizer are supposed to commute with only that element. Center, elements of the center of the group are supposed to commute with every element of the entire group. Okay? Again, let's take the same example, D3. Okay, now maybe before D3, more simpler example. Let T be an abelian group. In that case, what is the center of the group?
G.
G.
Okay, so this is again a result that is true for every abelian group. Okay, let's then go to the next example, D3. So what would be back to the table so that you can observe it.
Identity must be.
Identity will be there, right? Again, so that's identity no matter, and this is again a more general result, right? So I will always be E is always a member of the set. That's one trivial result that we can show. Next, any other element in D3 will it be in the center? Would R1 be an element in the center?
No, sir.
Why?
Sir, because R1 of R2 is not equal to R2 of R1.
Oh, it is. Otherwise,
But it is not commutative with the FAFB.
F. So R1 with FA. What do you get? Get FB. Similarly, FA with R1 you get unfortunately FC. Okay, so that is why, for example, R1 is not in the center. Then, how about R2?
So only identity will be
The
centered.
identity. Do all of you see that? I mean, for example, let's look at one of these flips. Why would FC not be a member of the center?
FC R1 not equal to R1.
FC R1 is and R1 is. Then they are not the same. Therefore, FC cannot be in the center. Okay? So in this case, the only element in the center is I. Probably I should have brought in more examples. It's just that examples make sense if the group is small, and although we have not proved it, you may have heard it in the tutorial that of course here any abelian group, it's not interesting to look at the center, right? Because the center is the entire group, so we need non-abelian groups. In non-abelian groups, one can have only once the order is 6 or above. Then the example becomes a little clumsy to handle. Okay, so as of now, let's just do this one example. But although the example doesn't imply much here, because it is the trivial subgroup, but we can in general show this result. Center of the group for any group is always a subgroup of the group. Okay. Once again, how would you put this?
Sir, this above proposition number 8 and the center of groups are in same statement only.
Which one?
That proposition 8 for all A belongs to G, and in here center of group for all Y belongs to G. So means they both are same only.
Is it? Is the same?
No, that proposition 8
It's down.
for all A
Oh.
belongs to G, and in
Ah. But for all A belonging to G is CGA, right? So this set will change if A changes, isn't it? So we saw a couple of examples here. CGR2, CGFC, they are different sets, right? But of course, proposition 8 states that this is a subgroup and this is also a subgroup. Proposition 9, on the other hand, is one set for the entire group, right? This does not depend on elements of G in the sense that I don't have to choose any element here.
Okay.
Given a group, this would be one set.
So we can say that it is like the cyclic group which change which element, and the generator are those which do not change, means which cover whole.
Once again,
Means we can relate it to that cyclic groups as it change with that element, like here centralizer and the center like a generator.
Not necessarily. Okay, let me ask this question. What is the relation between center and centralizer?
Means sir, in centralizer, if element changes, so it will be the subgroup only, but
But a different subgroup.
yeah, yes sir.
Possibly a different subgroup, not necessarily always, but
Yes.
possibly you will have a different subgroup. In this case, there is only one subgroup, right, that we are looking at, or one subset that proposition 9 says that one subset will always be a subgroup.
Yes sir.
Hello, sir.
Yes,
Sir, center is for a group and the centralizer is for an element, right?
exactly.
Answer the center. If a group is center, so it is centralizer.
No. Once again, if a group is center, that doesn't make sense. Can you
The
repeat
center
it?
of yes, the center of group is the centralizer of is the centralizer of group always, right?
No. What do you mean by centralizer of a group? Centralizer is defined for an element.
Any element in center will also be in
Will,
all the centralizer.
Right. So that is one.
Subset. Center is subset of
G will always be a subset of
equal to that centralizer.
centralizer for any element A, right? Right, because what does this say? It says all elements of the group that commute with a given element of A. ZG contains all elements that commute with all elements of the group, right? Not just with one element. So of course this has to be true. Okay, and somebody has written something in the chat. And all of you look at it and see if you agree with that.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Thinks it is the intersection of centralizer of all elements. Okay. So I hope you now see what is the difference between center and centralizer. Because of the names and of course the common concept of commutativity, it can be confusing. But it's just about getting used to these two different things, right? Clear?
Yes, sir.
Yes.
Okay, how do we prove this then? Same two axioms, closure and inverse. Closure, let AB belong to ZC. Next,
Sir, can we directly prove, like we have already proved that all the CG of A are subgroups of G, and in some lectures previous we had proved that if H1 and H2 are both subgroups of G, then H1 intersection H2 will also be
yes, but how many intersections can this have?
the number of elements in G, order of G.
So, order of G can be
infinite also.
infinite, right? So, that would be one problem we have to deal with, isn't it? So, the result we showed is given two subgroups H1 and H2, H1 intersection H2 is a subgroup. Here, unfortunately, you may have infinitely many intersections, right?
Yes.
Okay, so we have to be careful there. As far as the group is finite, then the result straight away holds, right? Because given a finite group, you will have a finite number of distinct subgroups, and therefore the intersection of subgroups, finite intersections of finite subgroups will also be a subgroup. All right?
Yes, sir.
How do we show closure here?
So we consider AB times X where X belongs to G.
Sir, I
Yes.
had a doubt. Sir,
Go
you
ahead.
said like for infinite we cannot say that infinite intersection we cannot say that it is a subgroup. But if we see by closure and inverse, it would be a subgroup. Sir.
So that's what.
Even
Yes. So the proof. I'm not saying that the result is incorrect.
like if we are going to see like closure, it will follow, and inverse also it will follow that. Like if A exists to
Right.
H1,
So that's
H2.
what I'm saying. So I'm not saying that the result is incorrect. Right? I'm not saying that proposition 9 is incorrect. But the way you prove it, you'll have to be a little careful if you're considering this intersection definition, right? That's all I'm saying.
Thank you, sir.
See, the statement may be correct, but you can come up with strange proofs, right? Which may be incorrect. Okay, that's all I'm trying to say. And again, I'm not saying this intersection thing is incorrect. You will have to deal with this infinite intersection a little carefully. That's all.
Yes, sir. Got it.
Can I assume you can complete this proof yourself? Just follows from along the same lines of the centralizer.
Yes, sir.
Yes, sir.
Associativity, etc., etc. You should be doing.
Yes,
You'll
sir.
be able to do it. So I'm giving this as a homework. Let's move on. And let's come to sort of a very important topic of this course, permutations. Okay, they are very important in the sense, I'll tell you maybe in the next slide. Okay, so before we do that, can somebody define what is a permutation?
The arrangements, all possible arrangements of number.
What is
group
a
of elements.
permutation? Is a permutation, not what are permutations.
Ordered arrangement of elements.
Ordered arrangement of elements. What does that mean? So if I take 3 elements, 1, 2, 3 in this order, then
We can arrange them in 3 factorial ways.
okay. Yeah, but mathematically, how do you describe a permutation? So intuitively, you're sort of again, it's not a new concept. It's basically a possible rearrangement of elements, right? That is a permutation intuitively. Mathematically, how can we represent it? So let's say
Element from the set of all possible arrangements of a ordered set.
all possible. So no, all possible arrangement, you're defining it as a set of all permutations. My question is, what is a permutation and how do I represent it? Let's say I have 3 objects, object 1, object 2, object 3. How can I rearrange it? One possible way, object 2, object 1, object 3. Right? If I take this, put this in a vertical order, right? The set, if I call the set of these objects as A, and this is also the set A, right? Remember, set has nothing to do with order, right? You can put the elements in any way you want, the set still remains the same. Now, how do I describe this?
Sir, can we say it is a tuple? N tuple.
Tuple. So in this case, can you explain?
Sir, in this case, sir, we can say that it is a three tuple. For three elements, it is a three tuple where the elements of the tuple are belonging, means are one of the elements that we are that are in.
Yeah, but so this is one permutation, right? I hope you agree.
Yes.
So how? Give me the three tuple that describes this.
Sir, O1, O2, O3. O1, O2, O3.
So how does this represent? So if I don't give you this picture, right, and you give me this three tuple, how can I find out that this three tuple represents this particular permutation?
Sir, we can define that the first element is at the top. Is at the top. Then O2 is at the second row.
No. So this is the original arrangement of objects, and now I am permuting this three and getting this rearrangement. So with this sort of a representation that you just gave me, how can I figure out that it is this particular permutation that is represented by
Sir,
this?
the order in which we write will distinguish the different arrangements.
Okay. So instead of this, you will write it as O2, O1, O3.
Yes, sir. Yes.
Okay, fine. So again, this is a representation. Mathematically, how do what is this doing, permutation?
Sir, we can say that for a set A, another set B of same size, and the order of each element is same in the set B also.
Is that a permutation there? If the orders are same, so in this case you write.
No, I mean the frequency of every element is same in B, and the size of the set A is equal to set B.
Domain is same as codomain.
So domain. So when you are mentioning the word domain and codomain, what are you talking about?
Elements on which we are
Talking of functions, isn't it?
Yeah, yes, sir.
Right? I mean, when you mention the word domain, codomain, that means you're talking of functions. So can a permutation, I hope the color is visible, I'm not sure. Question is a permutation a function?
No, sir.
No? Why?
Because it will be random permutation, right? It will be random.
So what do you mean by random? So for
It's
example, here if I give you three objects, right, O1, O2, O3, right? What do you mean by, so this is a permutation, isn't it?
Yes, sir.
So can't I see this as a function?
No, sir, because in function each element should map with some other element, and here no mapping is there.
Why is it not there? And O1 goes to O2, O2 goes to O1.
Yes, sir, we can
Yes,
think
sir,
of
but
it as map function.
but if there is but here there is another possible way to arrange.
So that would be another function. So
Yes, sir, it is a function.
A permutation, right? I'm not talking of set of all permutations. So instead of this order, right? You give me any order you want, O3, O2, O1, right? This is also another permutation, different from the previous case.
Yes, sir.
Can't I represent this as a function?
Yes, sir. Any bijective function.
Okay, so you've given me more than what I asked for. So first of all, you must, I hope, agree that it is a function. And a function f from A to A. Right? If I'm interested in permuting the set A. Okay, permutation on a set A can be represented as a function from A to A. Now, can it be any function?
It
Should
has
be
to be
by
one
one.
to
It
one.
will be 1 to 1.
Yes.
One to one. Not on to?
On to also.
If it is not on to, that means taken away one object, isn't it?
Yes, sir.
Okay, so 1 to 1
Bijection.
and on to which basically bijection. So that is what a permutation is basically. Right? A permutation of a set A is nothing but a bijective function on A. Is this clear to everyone?
No, sir, it is not clear to me.
Okay, what is your doubt?
Sir, means a permutation is just one. It is just one. What we say, one arrangement. So
Right.
how functions are involved? Because how functions are involved?
Okay, so let us take an example, maybe, right? Let's say the set A has, I don't know, 3 elements or 5 elements, whatever you want. Right? Let's call them. And of course, I hope you realize here that what are the elements of this set is.
It is not material.
It does not matter, right? So 1, 2, 3, 4, 5. Give me one permutation of this. 1, 2, 3, 4, 5.
3, 4, 2, 1, 5.
3, 4, 2, 1, 5. Okay.
Yes.
So here you have your set A, right? Your original set. Now, after rearrangement, you still have the same set, right? The set does not change.
Yes.
Okay. Now what you're doing? First element, right? That you are calling as 1. That is now replaced by the third element, right?
Yes. But here in set, the order is not material.
Order is not material, but order is something that you want to capture, isn't it?
Yes, sir. Yes.
Okay, so I still stand by this statement that in the set the order doesn't matter, but the order is something that you want to capture. That exactly is permutation, isn't it?
Yes, sir.
So how do I capture that order? Right. So whatever was originally in the first place now goes to the third place. Whatever was there originally in the second place, it goes to the fourth. Third goes to the second. Fourth goes to the first. It stays as it is. Right?
Okay, sir. Yes,
So,
sir. Yes. Sir.
I can just write this as f maps 1 to 3, f maps 2 to 4, etc., etc. 5 f maps 5 to 5.
But that way we can get only one permutation of A, right?
Exactly. Now give me any other permutation.
Suppose we take 4, 3, 2, 1, 5.
4, 3, 2, 1, 5. Take another function G. G maps 1
yes.
to 4.
Yes. I see it now. I see.
Okay. So that's why I was emphasizing on this question. What is a permutation?
Yes, sir. Yes, sir. Means what we say the it maps from places to another places, one position to another position.
Yes.
Yes. Yes. Now it is clear to me. Thank you, sir.
Okay.
Thank you, sir.
So can't we make a common function for all permutations?
How? So how does one function represent both these permutations? Let's forget all permutations. I give you these two permutations, right? This is first, this is second. How will one function be able to represent both these permutations together? Right? The definition of a function is for every element in the domain, there must be one and only one element. Right?
Yes, sir.
The person was asking the question. I hope I
Yes. Sir, I read somewhere that we can make a common function for next permutation, like lexicographically next permutation.
Lexicographically next permutation. I'm not sure if I understand your question. So
Like 1, 2, 3, 4, 5. Then its next permutation would be 1, 2, 3, 5, 4.
and what do you mean by next permutation? Why is that the next permutation? And how do you order permutations?
No, sir. I'm not ordering that permutations, but I'm ordering its elements. Like 1 is less than 2, 2 less than 3, 3 less than 4, and 4 less than 5. So, in that manner.
So, but when you are saying the 1, 2, 3, 4, 5 goes to 1, 2, 3, 5, 4.
Yes, sir.
Okay, then.
Then 1, 2, 5. I'm not sure on this.
1, 2, 4, 3, 5.
So even if it is 4, 3, 5, see.
We are considering it as a ascending order. We are considering them as a number.
No,
fine. 1, 2, 4, 3,
considering them as number, that's fine. But for me, this particular thing, this rearrangement is one permutation. This is another permutation, right? This is another permutation.
So this group is made up of numbers, so it is easy to.
No, first of all, there
consider
is no
them
group
as a
here.
number.
This is just a set.
Set, sorry, sir, set.
Okay.
But if we consider a D3 dihedral group of 3,
Okay.
then how can we arrange them? Means in order. Means how can we say that one some element is less than other element, or like?
So, but why should we say that? I mean,
So I am asking to Nisad. He is saying that we can arrange them like that. So.
But I think you're mixing two different things. Permutation of a set and this D3 is a group, right? I mean, why are you mixing these two? Here 1, 2, 3, 4, 5 can represent any object, right? And there is no binary operation defined over this set at all. We are looking at it just as a set.
Okay, sir, got it.
Once again, to the person who originally asked this question, I'm not would like to hear from him. Is this okay, or is the doubt still there?
No, sir, it's okay.
Okay, fine. Okay, so I hope I have convinced you, hopefully not by force, that a permutation of set A is nothing but a bijective function on that setting. Okay. Next obvious question is then, I hope you know all these terms, right? What is a one-to-one function? What is an onto function?
Yes, sir.
A discrete math course, right? So this is sometimes also called an injection. not the one that you hopefully have got during vaccination. Onto is also called a surjection. Okay? Right. So there, the obvious question is, if I now consider the set of all permutations on a particular set A. Okay. Eventually want to see if this is a group, right? Set of all permutations on a set A. Okay, please be careful here. So one permutation is represented by one function, a different permutation by a different function. If I consider all these functions, all bijections, right, and I want to make it or try to see if I can make it into a group. So I will have to define what else is needed for a group apart from a set?
Operation.
Operation. So what would be that binary operation?
Mapping.
No.
So
My set itself, exactly. My set itself contains mappings of functions, right? So the binary operation would be, as somebody just said,
Composition.
Function composition. Okay, so question is, does the set of all permutations on a set A is denoted by S subscript A together with the function composition, does it form a group? How do we verify this? Verify the truthness of this statement.
Check all 4 properties.
4 properties. So, right. So let's take them one by one. First property, closure or identity, whatever. And which one do you want?
Closure.
Closure. So let f and g be 2 functions from this set. I want to see if f composed with g is also in this set or not. So what is it that I have to verify?
FOG belongs to SA.
SA, but what does that mean? How do I show that FOG belongs to SA? What is it that I will have to show in order to show this?
FOG is also a function.
So, I mean, if you compose 2 functions, you will of course get a function, but
which is one
FOG is also permutation.
So F function is a representation of a permutation, right? And what sort of functions are permutations? It's written in the slide. Bijection. So we need to show basically that FOG is 1-to-1 and onto. Given that, of course, F and G are 1-to-1 and onto, right? So how, I mean, do you want me to do the proof or will you be able to complete it? Maybe we can do one of the 2. Which one do you want me to do it in class? The other you can do it yourself. Of course, if you want to try out both, then I would be happy. If nobody speaks, then I will leave this as a homework.
We'll try.
Okay, thank you. Okay, but the result is, of course, that FOG will be in SA. So it is closed. Okay, so I've just written the conclusion. Next, the function composition, right, is associative, right? You can prove this as well. Okay, so I'm leaving this as an homework. Third one, inverse. How about this? This is just a one-line proof, isn't it?
Sir, if F is bijective, then F inverse is also bijective.
Exactly. F inverse exists and it will also be bijective, right?
Yes, sir.
Yes, sir.
So just write this. Great. Anything else that we need to show?
Sir, the identity.
Identity. So what would be the identity?
So the function that maps the arrangement to itself.
Exactly. So that we denote it as the identity map. From A to A, which is defined as identity on A gives you A for all A in A. Okay, once you have defined this, you can verify that this is actually satisfying. FOID equals ID composed with F equals A. Okay, it's not very difficult to verify this. So therefore, ID, since ID, the way it is defined, is a bijection, there is this in SA also. All right. Any doubts?
Excuse me, sir.
Yes, go ahead.
Sir, I did not get that why it has to be bijection to be a part of that group.
Why? Because what is a permutation?
It is a bijection.
Bijection, right? So how do we define this set? SA is the set of all bijective functions, right?
Okay. Understood, sir.
Oh. Right. Any questions with this? Fourth axiom, identity. No. Then what is the conclusion? Just prove that a set of permutations on a set A along with function composition forms a group. Okay, and in case the number of elements in the set A is some n, right? We usually call SA is the symmetry group of degree n. All right. Okay, this is just a standard terminology. This is something we've already seen. So what are the elements of the set A? We don't care. So by default, given that SA has n elements, we'll always depict those n elements by integers from 1 to n. Okay, and usually also the symmetry group of degree n will be denoted by S subscript n whenever this A is not specified. Right? These are just notations. Okay. Yes.
Sir, sir, here SA comma composition is a symmetric group in the sense that the relation of composition is symmetric.
No. There's nothing to do with commutativity or anything. Okay, it's just a name, symmetry group of degree n.
Sir, because if FOG is belonging to SA, then GOF is also belonging to SA.
Yes, but FOG is not necessarily GOF.
Yes, they both are not necessarily equal.
Right. So GOF is in SA, that comes from closure, isn't it?
Yes, yes.
Right. Not from commutative.
Okay, so then what does the symmetric group imply over here?
So symmetric in the sense that it leaves the set A as it is. How did we define symmetry group of a triangle?
Yes, means we are getting the same triangle, just
Exactly.
with the different position of vertices.
Right. So similarly, as a set, right? Permutations are not changing the set.
Yes, yes, sir. Yes, sir. I got it. Sir.
But sir, in example of triangle symmetries, it it is not called a symmetric group of degree 6. So
yeah, it's not.
If we find another symmetric group of degree n, then how can we relate means?
So there is no relation between that example in the geometric example, right? Symmetry of a triangle and this symmetry group. I'm just trying to justify this name.
So the symmetric group of degree n is only a set of
permutations of a set which contains n objects.
So there are no other examples of symmetric group, right?
Right. Yes.
Okay, sir.
We do say, I mean, when you are talking about the dihedral group, we also call it the group of symmetries of a triangle, right? But that in principle is, I mean, although it is related to permutations, but we are looking at the geometric figure there. Is that clear?
Yes, sir.
Right. I think this is a trivial question, which I think someone already answered. What is the order of this group, SN?
N.
N.
N
Why
factorial.
N?
So it is n factorial.
N factorial.
N factorial, right? Not N. How do you show that?
Because the number of permutation is n factorial.
So that's what I'm trying to ask, right?
Yes.
How many permutations are there of a set containing n elements? That's n factorial, but you do need to show that, okay? And it's not very difficult to show it. I hope you can prove that.
Yes, sir. Yes, sir.
Right. So first element, how many ways are there to replace this? N. The second one?
n minus 1.
N minus 1. Final one is why this is it. Okay. Let's look at notations. So let's consider an example S8. Okay, means once again symmetry group of a set that has 8 elements. Since the set A is not specified, we'll assume the set A is 1, 2, 3, right up to 8. Now, if I pick one permutation from S8, right, this right hand side is how we will denote the permutation. Okay, so we'll denote it by a 2 by n array. First element, the first row is like the domain. Okay, so take this as the original arrangement. Okay, and the bottom row is the new arrangement after you apply the permutation. To interpret it that way. Okay, so 1 goes to 2, 2 goes to 6, 3 stays as it is, 4 goes to 5, 5 goes to 1, 6 goes to 4, 7 stays as it is, 8 also stays as it is. Okay, is the notation understood?
Yes, sir.
Now, we have a result to prove which says that each permutation that I pick in SA, it induces an equivalence relation on A, okay, on the set of objects A. What is the relation? The relation is two elements of the set A, let's call them P and Q. They are related to each other if and only if Q is obtained after any number of same permutation sigma on the element P. Okay, once again, right, given a permutation denoted by sigma, okay, two elements of P of the set A, calling let's note them by P and Q, they are related to each other if and only if, let's start applying this permutation on P. Okay, now you can reapply the same permutation on the resultant. So if sigma P denotes the result of applying this permutation sigma on P, I can apply sigma again on this, right? This is your sigma squared P. Keep on doing this, right? So you have P, sigma squared P. Continue this, sigma to the power NP. Keep on doing this, and of course K is in Z. And we have already proved that this is a group, so you will also have sigma inverse P. And reapply sigma inverse to get sigma minus 2 P. And keep on doing this, right, for any n. If one of these elements is equal to Q, say sigma Kp is Q, then P and Q are related. Otherwise, not. I hope the meaning of this relation is clear. If P and Q are related to each other if keep on applying the same sigma on P, sigma inverse also, keep on applying it on P and its resultants. In case one of these elements is Q, then P and Q are related. Understood?
Yes, sir.
Okay, now how do we show this? So what do we need to show if I have to show that this relation is an equivalence relation?
So to show that it is reflexive, symmetric, and transitive.
Okay, so let's do this one by one. Reflexive?
So yes, P is in relation to P, sigma raised to 0 of P.
Or P is related to P. Next. How do we show that it is symmetric? Let's say P and Q are related. What does that mean?
P is equal to sigma raised to K Q.
There is a K in Z
That exists.
that Q is equal to sigma Kp. Then
P is sigma raised to minus KQ.
Right.
And minus K belongs to Z. Therefore, P is in relation to Q is in relation to P.
transitivity. P is related to Q, Q is related to R, Q is sigma to the power some M times P, and R is to the power n times q. Then
R is sigma into n power plus n plus n power
okay.
of P.
Therefore, E is related to okay. So, for example, in this case, can you find the equivalence classes? This example. What would be the equivalence classes? Anyone? Okay, let me take the simplest case. What would be the equivalence class containing 3? Anyone? See, I can reinterpret this in other way, right? With this understanding, what all elements is P related to? P is related to sigma P, P is related to sigma squared P, so on and so forth. Similarly, P is related to sigma inverse P, sigma to the power minus 2P, so on and so forth, right? So at least this question, everybody should be able to answer very quickly. What is the equivalence class that contains the element 3? Okay. So what is sigma 3? Hello? Have I lost
Sigma power minus 1 of that Q.
No, so what is sigma 3? Sigma applied to 3, where does it sigma map 3 to?
itself.
Itself.
3.
Right? So where will sigma inverse map 3 to?
Itself.
Itself. Sigma squared?
Itself.
Itself. So what other elements can there be in the equivalence class of 3?
No other.
No other elements. This is an equivalence class by itself. Similarly, 7?
7 and 8. I mean
7 and 8?
No, means 8 also is
a separate equivalence class. Then what is the equivalence class containing 1? 1 goes to
2.
2 will be there.
2,
Okay?
6, 4, 5.
Goes to 6. 6 goes to
4.
4 goes to 5.
And then term.
That's all, right? Okay? In the context of group, these equivalence classes are given a new name. Each equivalence class in the set A for a particular permutation sigma, these are what are called orbits of sigma. Okay, just a new name. It's like you have planets in your solar system under some force, right? They are going through places. All points through which a particular planet passes is usually called an orbit, right? So the same concept holds true over here. Instead of force, you have permutation, a particular permutation given to you which acts on a particular element. All elements that you get by applying this permutation again and again, right, are elements of what we call orbit. Right? So that's the analogy. Orbit of a planet, orbit of a permutation. Right? I hope it makes sense. I think this is the last definition we will do this class. So let's say I give you a permutation sigma, right, on a set A. This permutation is going to be called cycle. Okay. Right? If an if condition here, if there is at most, okay, please be careful here, at most, if there is at most one orbit with more than one element in it. Okay, it's again a permutation sigma is called a cycle if there is at most one orbit which has more than one element, and then number of elements in that orbit, in that particular orbit, is called the length of the cycle. Okay, so let's just look at this example sigma given on the top of this slide. Is that a cycle?
Yes, sir.
Why? Because we have just found out the orbits, right? What were the orbits? Right? In all the orbits, right? How many orbits are there which has more than one element? It's only this particular orbit here. Okay, so therefore, this sigma is a cycle. Okay, and what is the length of this cycle?
5.
Here. Oh. Cycle of fine. Okay, so cycles are a particular kind of permutation, right? If that permutation has only one orbit which has more than one element, at most one orbit with more than one element, in that case that permutation is called a cycle, and the number of elements in that orbit is what is called the length of the cycle. Okay, we sort of continue from this, right, and try to study permutations using cycles. Because cycles are sort of simple permutations in the sense that most some of the elements possibly remain the same, and any elements whose place gets changed is in sort of the largest orbit. Okay, so we look at more examples and then take this concept ahead. Thank you, and see you guys on Tuesday. Right? Right, the tutorial will be available for you to work out hopefully by today afternoon. Okay. Stop the recording. Don't have any questions, can leave. If somebody has any questions, please feel free to ask.